for some people to trickle in. Why don't you turn to your neighbor and tell them which talk and conference was your favorite? For the first time in forever, it wasn't Peter Uchtdorf. Usually it's always the beater. But at our ward Halloween party, I'm in charge of a game called Peter or Dumbledore, where we have quotes and they have to guess whether it was Peter or Dumbledore. So tell your neighbor which talk was your favorite.
It's gonna be a good day after all. You know, I thought today was a song, but no, here I am drinking a Red Bull at 9 a.m.
Dumbledore. 60 boys. Okay.
No, I don't need to. Eric. So what I'm hearing is
We
working out tonight, I guess.
we have 2 sample exams with their solutions at the MAC site. And in addition to that, I hope you all got the email from Dr. Benyon about the online exam. And I apologize for those of you that heard this earlier before class started, but that online exam is just the midterm from winter semester. I just handed that midterm from winter semester to Dr. Benyon and asked him to make that online exam. Now, we're not giving you the solutions to that because we want to recreate the experience that you have in the Learning Center. Many of you said that, you felt you understood the material for the first midterm, and then you got to that exam and were blindsided. Well, we don't want that to happen. We want you to know going in how that experience is going to play out. And if you can take that online exam as many times as you want, and if you just keep on getting 80% on that, I'm pretty sure you're going to get 80% on your midterm. Okay. If you want to know how to solve the problem, there you can go to the other 2 sample exams where we give you the solutions, and you can see the steps that are involved in solving different kinds of problems. But if you just want to, get a feeling for how prepared you are, that's that online quiz. Questions about the exam? Or I'm going to be in this room tomorrow evening at 7 o'clock answering any questions you might have. I will record that session and post it to YouTube and send out a link to everyone if you can't attend. I understand there's all sorts of homecoming things going on.
What does it cover?
The exam will cover dynamics, which is a study of forces. So today's lecture on tension and the last part of today's lecture will be a kind of a overview, kind of a review for the exam. Today's lecture will be on the exam. On Thursday, we're going to start our study of energy, not going to be on the exam. Okay, so today's lecture will be on the exam, but today's lecture you already know, because today's lecture is about that tutorial, and you all loved the tutorial, didn't you? No one cried during the tutorial? Good. Okay. Okay, I think we're all here, so let's take some attendance. Okay, now you can click.
So funny.
Now it'll work.
Yeah.
Okay, last call. Okay, good. We haven't seen that many problems involving magnets. And so I'd like to just give you a sample problem and work it on the board. Well, tell me, Randy, has someone beaten all the refrigerator magnets again? Yeah. Okay. So this sample problem involves a refrigerator magnet. And we're using that refrigerator magnet to hold a business card to the refrigerator. And we're asked to draw free body diagrams for both the business card and the magnet. Now, since we're drawing free body diagrams, we're going to need some space. And so which diagram should I draw first, people? So I'll speak up on one.
Okay.
Thank you. Oh, I love you people. Okay. So we've got the business card. We've got the magnet. Okay, so let's follow the recipe. The first force I put on any diagram is the weight force, Earth on the magnet. And that's just the mass of the magnet times G. We're told that the mass of the magnet is 25 grams, and I multiply that by 10 newtons for each kilogram, and that's going to give me 250 newtons. Wrong or sick and wrong, people?
Wrong.
Yeah, a newton's only a fifth of a pound, but hey, that's a 50-pound magnet. That's probably not reasonable, right? Clearly, I have to convert the mass of the magnet. Whoa, that was the mass of the business card. I made it bad. This was 50 grams. My bad. The mass of the magnet is 50 grams. And I have to convert that into kilograms. If you're buying a kilo of something, all the students at Montana State know what I'm talking about. What, Tuesday after conference? You move the decimal place 3 places over, and so that's going to be 0.05 kilograms. And so I would do that again with 0.05 kilograms times 10 newtons for each kilogram. And that's going to be half a newton. And that makes more sense, does it not? And I'm going to make that just a little bit longer. Now, once I put the gravitational force on my diagram, I ask myself, are there any magnets in this problem? Whoa, finally, yes, yes, there are. So, how should I draw that magnetic force? Well, the way we're dealing with magnets, we're dealing with them as attracting to refrigerators. We're going to find out in 106 that they can also repel, but we're not going there. Not until we get to 106. Okay, so it's just an attractive force where the magnet and the refrigerator are attracting each other. But I'm looking for the force on the magnet, and it's attracted towards the refrigerator, so that's going to be a force to the left. And I'll label that with an M, refrigerator on the magnet. And now I've done all of the non-contact forces. And so now I ask, well, what touches the magnet? Well, only the business card. Does it push or does it pull? Not a string, not a thread, not a chain, not a rope, so it must push. Whenever one thing pushes on another, there will always be a normal force. This would be by the business card on the magnet. And by normal, I mean perpendicular to this surface between the pusher and the pushee. And since the pusher, the business card, is to the left of the pushee, that force is going to be to the right. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. Do I need a friction force in this case? Yeah, we're told that nothing goes anywhere, and that diagram screams down to me. Now, a friction force has to point parallel to the surface. That could be either up or down. I definitely need a force that's up. That's going to be a static friction force by the business card on the magnet. Now, I know that this diagram has to screen balance in both directions. So I know that this force has to be also half a newton. So far, so good? Now we go to the business card, and its weight force, since it has half the mass, that's going to be 0.025 kilograms. Since it has half the mass, it's going to have half the weight, and so that's going to be a quarter of a newton. Now, folks, whenever you're drawing free body diagrams for things that are touching each other, when you get to the second diagram, use Newton's third law. The business card cannot push. Oh, first of all, are there any magnets in this problem? Are there any magnetic forces on a paper business card? No, no. Okay, so let's look at the contact forces. The business card cannot push to the right on the magnet without the magnet pushing back just as hard with a normal force. And that's going to be the magnet on the business card. And I'm going to put a tick mark here and a tick mark there to say that those are third law companions. Also, the business card cannot push up on the magnet with a friction force without that magnet pushing back just as hard, also with a static friction force. And I'm going to put 2 tick marks there and 2 tick marks there. Then I asked, what else is touching that business card? Well, the refrigerator. Does it push or does it pull? It pushes. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. In this case, I definitely need a friction force. It'll be a static friction force. And since there's no acceleration up or down, this one has to balance both of these forces down, which is going to be 0.75 newtons. Okay. Now, folks, this is an old exam question from the before time. Okay. And not many people in the class got it right. And the force that they left off of their diagram was this one here. So it's helpful, even if you're not asked to look for third law companions, even if you're not offered any point for looking for third law companions, go looking anyway to make sure that you haven't left any forces off of your diagram. Because I will tell you this, if you have the wrong free body diagram, you have zero hope of getting the right answer on the problem. There is no way to recover from that. Everything else you can repent of, but a wrong free body diagram, not in this world or the world to come. See if your neighbor's on the bus.
Everybody diagram on the bridge. You got like Earth, normal, nothing left. Function left. Sees the normal course of the plane.
Oh, weird though. Like it's not, I guess that makes sense. Not possible.
Okay,
Occupied diagrams, I just think about it in my head.
now, if this magnet had a magic knob that I could twist and make the magnet stronger, but it didn't affect the mass of the magnet, just the strength of the magnet. Well, I would expect a stronger magnet to pull harder. That's why I would pay more money for a stronger magnet. And that means that this magnetic force is going to get bigger. Well, in order for this diagram to continue screaming balance, that means this normal force would have to get bigger. If this normal force gets bigger, by third law, so does this one. And in order for this diagram to scream balance, so would this one. Imagine that you had a really skinny finger and your finger was between the business card and the magnet. When you turn that knob and make the magnet stronger, you would expect that to hurt more, okay? And that's the normal force there, okay? Squeezing your finger. What about these forces, the vertical forces? How do they change? Not at all. Not at all, okay? And I want to point something out. When you have a magnet holding up your artwork onto your refrigerator, if you had a perfectly vertical refrigerator that was also perfectly frictionless, no magnet in the world could hold up your artwork. It'd just slide down to the floor. It's that friction force right there that's holding up your artwork. Okay, not the magnetic force, that's in the wrong direction. Questions on this problem? I happen to know there are a number of problems on the exam that involve magnets. Just always think of them as attractors that are attracting to something metal, okay? And find the metal they're attracted to and put your arrow in that direction. Okay, let's move on. Okay. Does that bring back good memories? Yes, it does. I love this tutorial. Remember, I was the first teacher on this planet to take this tutorial into the classroom, clear back, oh, so many years ago in 1991. And I got to tell you, that was an experience. That I came back to Lillian's office and said, whoa, that didn't go well. So let's talk about it. Let's talk about that. You are told that the hand pushes with a constant push and that the table is frictionless. Now, your experience has led you to believe that that's going to give you a constant acceleration. Let's put a number to that. Let's say that's 3 meters per second squared, and it stays 3 meters per second squared. That's what we mean by constant. Always stays the same. Now, you were asked to draw 3 body diagrams for block A, block B, and the heavy rope. Now, the diagrams I'm going to put up right now are not right. Don't be copying them down. They're wrong and sick and wrong. But they're the diagrams that you put down, most likely, when you were in tutorial to begin with, okay? You said, oh, the earth pulls down on A and the table pushes up on A. Oh, and the rope is pulling to the right on A. On B, I've got the weight pulling down and I've got the table pushing up. Oh, and I've got the rope pulling to the left and the hand pushing to the right. Oh, and if the rope is pulling to the right on A is pulling to the left on the rope. And if the rope is pulling to the left on B is pulling to the right on the rope. Oh, and it's a heavy rope. And that's where most of us started our free body diagram. And then if your instructor was doing his or her job, they came over to your table and they said, oh, just a moment ago, you told me that the acceleration of this whole thing was to the right. Well, that screams to the right. And I guess that screams to the right, if that's bigger than that. But that doesn't scream to the right. And so you fix it. Watch. Everyone watch. Here we go. Pow! Fix it good. And then if your instructor was doing his or her job, they said, well, yes, that is a screen to the right. But what about this primal screen down? What's that about? And so again, you fix it. Watch. Pow! Okay. Fix it good. And then if your instructor was doing her or his job, what they then did was they challenged you to find a boogeyman. What thing that you can taste, smell, touch exerts that force on the rope? And if you can't find a boogeyman to explain that force, it don't exist. Okay? That's one of the most important tools in your toolbox. If you can't find a boogeyman, that force doesn't exist. And that's one of the reasons we label all of our forces. Okay? The other reason is to find third law companions. So at that point, you had to get rid of that downward screen. And I hope you noticed that that heavy rope is sagging. And indeed, if you have a frictionless table, you can't get rid of that sag. It's impossible to get rid of that sag. And a rope can only pull in the direction of the rope. And so that means these forces acting on the rope have to be up at an angle. And this component here and this component there combine to get rid of that downward screen. Is that where you ended up? And now, if this force is up and to the left, by third law, this force has to be down and to the right. And now I have a question for you. If this weight force is 50 newtons, how big is this normal force? 50 newtons or bigger or less? It's got to be bigger because this force has to balance both this component and the weight. So I have to make that bigger, okay? Now, likewise, if the rope is pulling up and to the right on B, B's pulling down and to the left on the rope by Newton's third law. Again, this normal force has to balance both the weight and this component. So it has to be bigger. And since I made this one bigger, I've got to make that one bigger. Those are the correct free body diagrams. That's where you were supposed to end up. Those are the truth that you are now ready for. Now, on the second page of that tutorial, where all the thinking happened, that's where all the sweat happened, was on that second page. What we do on that second page is we wave a magic wand and we say Expelliarmus Windosa. Okay? Anyway, we magically change that heavy rope to a light string. And we're asked to do that in such a way that the acceleration stays the same as before. If it was 3 meters per second squared before, scooting across the table, it's the same now. So what does that tell me about the force by the hand? Tell your neighbor, is the force by the hand going to stay the same or is it going to change?
The weight force goes down.
That force there.
Mass accelerate the force by the hand the same. Your reasons.
Okay. If the mass of the whole system went down, got smaller, and I want the same acceleration, the push by the hand has to get smaller. So I know that this force is going to change. The question you were asked on that second page of the tutorial is, how many other forces are going to change? Okay. If that's the rope, how many different changes can you find? And we're going to play a game. You're going to count the changes. You're going to vote. And this is the way we're going to count the changes. If this force, if this component changes and this component changes, that's two changes. Okay. But if this component changes and this one doesn't, that's just one change. Everyone on board? Okay. So the question is, do you see 8 changes, 9 changes, 10 changes, 11 changes, or more than 11? Talk to your neighbor and then vote with your clicker.
Of the top ones, obviously. Every single force for that change. And then 10, 11, 10, 11.
So the mass word again, if it's small.
And by themselves.
That's good one.
On A, if I did rather be. Yeah, yeah. One going, I have. Rope going up, we're gonna get shorter, right? Yes, so those are the hands get shorter, which means it develops in the next direction, it also makes sense. Point away, that's six, and then catch on and.
Okay, let's get your vote in. If you haven't voted yet, get your attendance points. Okay. Last call. Whoa. We're all over the map, people. We are all over the map. Let's do it together, shall we? Let's start over here. What about this force? No, only diet or exercise can change that one. What about this one here? Okay, so that's one. What about this one here? That's two. Folks, unless someone asks you to marry them today, the next question I ask will be the second most important question you receive today. Okay? So what about this one here? Yes or no? Shout it out. No or heck no?
No.
No. Why? Why? Folks, when you're reasoning the why in this part of the class, it's always with Newton's second law and a free body diagram. I got my free body diagram. If I use F net equals MA, and I'm doing this on A. So this would be the mass of A and the acceleration of A. We were told that the hand pushes in such a way that the acceleration stays 3 meters per second squared. This stays the same. The mass of A is not changing, and that means that the net force on A has to stay the same. Well, the net force is the extra force, the unbalanced force. And lo and behold, that's what this component is. That's the net force right there. And it cannot change. So I've got 1, 2. Let's go over here. What about this one? No, by third law, if this one doesn't change, that one doesn't change. What about this one? That's 3. What about this one? Yeah, that's given. That's 4. Okay, what about that one? That's 5. Now, folks, again, unless someone asks you to marry them today, this is the most important question you'll be asked. Oh,
I was gonna ask, why does the Y component of the tension,
what's that?
why does the Y component of the tension change?
Oh, because the diagram still has to screen balance in the vertical direction. And if I no longer have a heavy rope, but I just have a light string, this gets very, very small. And remember, these were there to balance that. And now I don't need very much to balance the weight of a very light string.
But how do we know whether A or B or both?
Ah. That's a good question. How do we know? Can I put that question on hold for just a moment and come back to it?
Yeah.
Because it'll make more sense when we go 2 slides further. Okay? Okay, let's see where we are here. 1, 2, 3, 4, 5. We're up to 5. What about this one? Does it change or no?
Oh.
Yeah. Yes. And again, our reasoning is with Newton's second law. Now, if we start with the heavy rope and we switch to a string, this would be on the rope. The acceleration stays the same, but now I have a tiny mass of a string, and that means my net force has to get smaller. The net force on the string has to be smaller than the net force on the rope. And so this stays the same, but this gets smaller so that my excess force gets smaller. So I'm up to 6 now. What about this one here? 7, that one, 8, that one, 9, that one, no, that one, 10. So the correct answer is 10. If you didn't get 10, slap yourself, please. Now,
And then. If he's.
Just because.
okay, now let's let Brother Gates, Bill Gates, show us all of these changes here. Okay, you're seeing all 10?
Richard, ask a question.
Now, at the bottom of that second page, we went from the light string to a massless string, a string that has 0 mass. And at that point, we go from that. Now we get rid of all of the weight and we get to those diagrams there that are almost the same as what you started with, except there's no weight force on the connector. Okay? Now, I have found in my experience that for some of us, it helps to use numbers. And so I'm going to make up some numbers here and put those in. You can see that with the heavy rope, I have a net force on block A of 5 newtons. That's the screen. How big is the net force on the rope? Tell your neighbor real quick. What's the net force on the rope? Okay. I've got 8 to the right and 5 to the left. That's a scream of 3 newtons to the right. The net force of the scream is 3 newtons. The net force on B, I've got 12 newtons to the right, 8 to the left. That's a scream to the right of 4 newtons. The net force would be 4 newtons. When I go to the light string, I still need the same net force on block A because its mass didn't change and its acceleration didn't change. I still need the same net force of 4 newtons on block B, again because its mass didn't change and its acceleration didn't change. 10 minus 6 is 4. But I don't need 3 whole newtons to accelerate a little tiny string. Maybe I only need 1 newton. This force can't change because that one can't change, but this one can get closer to that one to give me a smaller net force. And then when we go to the massless string, again, I have to have a net force of 5 on A, a net force of 4 on B, 9 minus 5. But if I've got 0 mass, it doesn't take any force, net force, to accelerate it. And what we learned in that tutorial is that if you have a massless string, I can have force on that string. I can have 1,000,000 newtons on that string, as long as I have the same 1,000,000 newtons at both ends of the string, so that the net is 0. A massless string has to pull the same at both ends of the string. Now, folks, every single introductory textbook in this class, for this class, always has in every one of their problems massless string. They just assume that from the get-go. But they never really explain why the tension, they always talk about the tension in the string, but they never explain why there's only one tension in the string, why there's the same pull at one end as there is on the other end of the string. Now, when I came back to Lillian's office after going through this tutorial for the first time ever in the history of the universe, I gave her some wise advice. I said, Lillian, put that rope right flat on the table, connect it right at the bottom of block A and block B, get rid of the sag, easy peasy. You'll get rid of all the confusion. She looked at me with a look of disdain. She would have slapped me if she could get away with it. And she said, Greg, the mess is the point. Struggling with that sag is the point of this tutorial. That's what's making you better people. You are better people now than you were last week. Most of you, okay? Call your parents, ask them if you're better people. Okay. Are there questions on massless string? Yeah.
Sending out a video.
So back to your question, before I ask your second question, let me answer your first question. You see that our goal was to eventually get to the massless string, and here both the left and the right have to have 0 vertical component. So it seems reasonable that as this string is getting lighter and lighter and lighter, that it gets smaller on both sides. Now, your second question is? No, the video for this tutorial we just had right now. Now, I do, right now, Sam is recording this lecture, and so if you would like a copy, just send me an email and I'll send you a link to it. Okay, but because I've gone through the tutorial step by step here, I did not make a video of the tutorial. Yes, sir.
Time. Rate of acceleration, mass acceleration are the same. On the right. Are the mass changes there. Like more than. Those are 8 and then those are 6.
Oh, Newton's law says that this equal sign should be read causes. A net force causes a mass to accelerate. And a net force is just the extra force. If my acceleration is to the right, I got to have more force to the right than I have to the left. And so that's what the scream is, the net force is how much of this is extra. 5 of this cancels that. I got 3 extra to the right.
Because it's accelerating to the right, that's what it's.
Yes,
5.
because this has mass and it's accelerating to the right, it's got to have more force to the right to the left. But when we get to the massless string, if I plug in 0 here, it doesn't matter what the acceleration is. When I multiply by 0, I get 0. Now, folks, up until now, I have encouraged you to draw a free body diagram of everything in the problem that is in the problem. But from now on, I'd like you to draw a free body diagram of everything in the problem that has mass. Never again draw a free body diagram for a massless string. Why? First of all, because it's boring. I got the same force left as I got to the right. But the real reason is it's confusing. I look at that and I can see the acceleration of the system. I look at that and I can see the acceleration of the system. I look at that and I'm confused. It looks balanced. And when I see a balanced free body diagram, I want to say, oh, that's 0 acceleration. That's not true with massless things. I could have any acceleration and it would still be balanced. So never draw a free body diagram again for a massless object. See if your neighbor is willing to do that.
I was gonna ask, is it?
Get those with the
Let's wait for them to
How is
start. Okay, everybody. We've got a question here.
I was gonna ask, is it possible to actually have massless things in the real world? Like, is that actually applicable or is it just theoretical?
Other things besides strings, you mean?
It's like in the real world, because like
Oh, can you have massless things in the real world? The real example of a massless thing is a photon, which makes up light. But the real answer to your question is that there are a lot of problems in which the mass of the string is very, very small compared to the mass of the rope. I'm sorry, mass of the block that it's connected to. And so there are a lot of problems in engineering and physics where you can ignore the mass of the string. But in truth, there's no such thing as a massless string. It's just very light. When it gets light enough, we call it dental floss, and then nobody uses it. Okay. Okay. Now, we had this pretest last day, and you were asked a question. You're told that first of all, that there was friction on this table. And you were told that the whole system was accelerating to the right. And you were told that the mass of book B was bigger than the mass of book A. And you were asked to compare the tension in string 1 to the tension in string 2. And this was the question you were asked. So let's vote again now that we've had the tutorial. The force exerted by string 1 on the little book is less than, equal to, or greater than the force exerted by string 2 on the big book. So
Watch, everybody's gonna get.
you look excited to do some helping. Okay. Get your vote in. Last call. Okay, the correct answer is greater than. Well done. Well done.
Here's my.
Now, for years, for many years, I was giving this pretest and collecting the papers and filing them away in a big cabinet until I had a mountain of these pretests. And I collected those pretests because I was trying to figure out what mistakes students were making to get the wrong answer. What reasoning were they using to get the wrong answer? And the more I looked, the more different ways I found that students got the wrong answer. And I got really discouraged that I thought, well, there's just too many ways to get this wrong. And then I noticed something. I noticed that nearly everyone who had a free body diagram on their page got it right. And nearly everyone who didn't have a free body diagram on their page didn't. Now, the lesson there is that there will be a couple of free response questions on this next exam where you are offered points for drawing a correct free body diagram. Draw the diagram, label your forces, collect your points. For most of the exam, since it's mostly multiple choice, there's no place for you to draw a free body diagram. You don't need to draw a free body diagram unless you want any chance of getting the problem right. Okay. So regardless of whether it gives you points for a free body diagram, you should have scratch paper there to draw a free body diagram, because that's always the first step. It's not busy work. It's not something you do for points. It's something you do to get the right answer. Okay. Now, suppose I had these three identical blocks. I got them at Lowe's, and they're connected by these two strings as shown. And I asked you to compare the tension in those two strings. The tension in the left string is less than, equal to, or greater than the tension in the right string. With your clicker, please.
Because the thing is,
Okay, get your vote in. Thank you, thank you. Last call? Good. The answer is equal to. Equal to. Whoa, I hear people saying, wait a minute, Greg. This one has two blocks pulling on it, and this one only has one block pulling on it. Or is that what you're saying in your head right now? Ah. The reasoning is always found in a correct free body diagram and then pointing at the free body diagram intelligently. If I draw a free body diagram for that block, let's say it has a weight of 50 newtons. If it's just sitting there going nowhere, the tension force pulling on it is 50 newtons. Excuse me. My phone goes right to my hearing aids. Okay. Which block did I just draw the free body diagram of? Yeah, all of them. It's the same for all of them. So if the tension is 50 newtons in this string, it's 50 newtons in that string. Now, if we think of what tension means, if you look at a chain, it's the pull of each link on each other. If you think of a rope, think of pulling the rope apart and inserting a spring scale. It's going to be the reading on that spring scale. But if you think of a spring scale, if I hold a spring scale here, I wish I had one to show you, and I hang a 6-pound trout on it, I want that reading on the scale to read 6 pounds. It reads how hard I pull on the bottom. It doesn't read how hard I'm pulling on the top. You know, it doesn't matter what's holding the top stationary, whether it's the wall or whether it's another block, it's the same. Okay, so the tension would be the same in both of those strings. Now, you were just given a review sheet that has all of the skills that you need to bring to that second exam. It also tells you when the exam opens and when it closes. Again, people, I cannot stress this enough. The testing center closes early on Saturday and early on Monday. Okay, it's your responsibility to make sure that you have enough time to take that exam. Okay. Now, if you turn that page over, can anyone see my clicker? Oh, there we go. If we turn that page over, and grab it. We have a situation where a block A, which has a weight of 50 newtons, is found to be pulled by a block B in such a way that it moves with constant velocity. Oh, I hit the floor. Okay, let's try this again. It's moving with constant velocity. Okay, let's say it is. I could have spent all morning balancing that so that it did, but I didn't. So we are asked to draw free body diagrams for both A and B. we're told that the incline is frictionless and that it makes an angle of 37 degrees with the horizontal. So which block should I draw the free body diagram of first? Shout it out. Thank you. Okay, so I have this weight force acting on B, and I don't know how big that is. If I knew how big that was, I'd know the mass of B, and that's the goal. But I also know that there's a string pulling on B. And that's my free body diagram. I'm done. And because A is going at constant velocity, constant speed in a straight line up that incline, B is going down at a constant velocity. So I know that this diagram has to scream balance. Let's draw the free body diagram for A. I have a weight force, and I'm told that that's 50 newtons. I then ask, what's touching A, because there's no magnets in this problem. Well, there's the string, and it pulls with a tension force. And there's the ramp, and it pushes with a normal force. Now, whenever I have a problem involving a hill or a ramp, I always want to rotate my coordinate system so that the x-axis is lined up with the hill. And then I find that all of my forces are lined up with my coordinate system, except for the weight. It's always the weight. Now, people, this is the most common mistake that is made on this second exam. People break up that weight force the wrong way. Turn to your neighbor and say, you'll do it wrong, but I'll do it right.
Make it a little string, like a little log.
Because if history is any teacher, half of you are going to do it wrong. And so, you know, one of you sitting next to each other was right. Okay, this is how you do it correctly. Look in the direction of the normal force and go the other way. Go in the direction of the negative y direction. And you go far enough so that you can take a 90-degree turn and get to the end of the weight. If you do this, do it that way, this angle here is going to be the angle of the hill. Now, if this is 50 and this is a 3, 4, 5 triangle, this is going to be the X part of the weight. That's going to be 30 newtons. This is going to be the Y part of the weight. That's going to be 40 newtons. Once you have broken up the weight into its parts, throw away the original and use the parts. In the Y direction, this diagram has to screen balance. So this has to be 40 newtons. In the X direction, this has to screen balance. That has to be equal to that. So this has to be 30 newtons. And now I use the law of massless strings. You're not going to find that law in any textbook. Not even ours, not even mine, because I was too ashamed to put it in there. But there is a law of massless strings, and that is that whatever pull I have on one end of a massless string, I have to have the same pull at the other end. Okay, so if this string is pulling on A with 30 newtons, it also has to pass pull on B with 30 newtons. And since this diagram has to screen balance, the weight of B has to be 30 newtons. And that means that the mass of B is equal to 3 kilograms. Now, again, this is an old exam question. And a lot of people got the right answer and then erased it and said that can't be right, because they knew that the mass of A was 5 kilograms. And they got their answer of 3 kilograms and they said, well, how can 3 kilograms pull 5 kilograms up the ramp? And the answer is the ramp isn't straight up. That little mass here doesn't have to balance all of the weight, just the part of the weight that is in the vertical direction. Okay. And so let me push that to extremes. If I take it down to an angle of 0 degrees, I could put a huge ship like the Queen Mary on here. If this was truly a frictionless table, I could hang just a simple little teaspoon from the captain's table on this end, and it would accelerate the big old ship. It'd be a very small acceleration, mind you, but with no friction, there would be a net force, and it would accelerate. Okay? See if your neighbor's on the bus, people. No child left behind.
Balance like what's that point vertical?
That
Attention.
Oh, let me answer that. Oh, the question was, if this diagram is balanced in the x direction, why does it move? Well, if it started from rest, it wouldn't. If I started this thing stop, it would stay stop. But remember, acceleration 0 can also mean going down the road at 100 miles an hour, as long as you've got cruise control on and the road doesn't turn. Okay? Acceleration 0 just means don't change your velocity. And so certainly we couldn't start from rest with this, but we could keep going if we started out going. Okay? And that brings us to the last part of this question, and that is, if a giant hand comes and stops this thing while it's going up the ramp, and then lets go, what would block A do? Well, as soon as the hand lets go, I go back to the exact same free body diagram that I started with. That's balanced. And so that means if I stopped that block, A, and then let go, it would stay stopped. It wouldn't go anywhere. It would have 0 acceleration. Yes, sir.
Your original works, are you able to rewrite your X component force diagram, or would that be inappropriate? Like, could you draw it like that?
The question.
Knowing something different.
Let me see if I understand your question. Are you saying, can I do this here?
Yeah.
Yeah, you can. I drew it down here to show that it's a triangle, but I could also say this acts that way and that acts that way. But this angle is not 37 degrees. This would be 53 degrees. And that's why I always do it this way. Okay? If I added friction to the ramp, now the tension would have to be big enough to balance these two. And so I would need a bigger tension force, and I would need to grab a bigger mass to make it go as constant velocity. Okay. Okay. Let's skip that. We're going to have a quick review, and whatever we don't get to, I'll do at the beginning of class on Thursday. Okay, so you'll get all of the review you need to be ready for that exam. So we've seen a whole lot of different dynamics questions. But there really is only one dynamics question, and we keep dressing it up in different ways. By the end of that second midterm, you're going to be so bored of writing F net equals MA that you'll just be sick of it, okay? Because we just keep solving it over and over and over again. Here's the one dynamics problem. I have a mass of block, a block of mass 24 kilograms. It's accelerating to the right 6 meters per second every second. And I give you some of the forces, like I give you the weight, that's just 10 times 24. But I haven't given you the third force or the fifth force. And so I want you, with your clicker, to tell me what the force 3 is. How many newtons is force 3? Work with your neighbor and vote with your clicker.
My head break.
Okay, that was not that hard. Please get your vote in. Last call. Still need a couple of clicks. Close enough. Okay, oh, you people are wonderful. You're ready. You're ready. Okay. So all we did was use Newton's second law in the vertical direction, in the y direction. Okay. All of the forces up we added as positive. All of the forces down we added as negative. And then we set that equal to the mass times the acceleration in the y direction, which was 0. And when we solve that, you get C, 530 newtons. Well, now let's do the harder problem. What is F5? Okay, again, with your clicker and your neighbor. And that's going to be different on the exam. You won't get to use your neighbor.
5. Yeah, net force. Boom. So it has to be 144. It has to be.
Not scared.
Yeah.
Okay, get your vote in. Last call. Okay, is that all of us? Okay, good, excellent. The answer is B. Again, we use Newton's second law, but this time in the x direction. And so this time it's not zero on the right, it's the mass times the acceleration. And for F net, I just add up all the forces, but I add them as vectors. If they're to the right, they're positive. If they're to the left, they're negative. And then it's just algebra. Then you just solve for F5 and you get 1036 Newton. Okay? And that is every single dynamics problem in the world. Okay? Now, folks, you were given a problem, the gauntlet, that I was hoping that we could go through today, but that just isn't going to happen. We should not start a problem like this with 3 minutes left. So what I would like you to do is make sure that you have tried this problem, seriously tried this problem, before you come to class on Thursday, and we'll start class with this problem. We're kicking off the homecoming over at the Marriott Center. It should be an e-ticket ride. Okay.